Yeah. Thanks. Yeah, so as you said, the talk is about distinguishing fillings using the dynamics of Fukaya categories, and in the main examples, in the main examples that we construct, the dynamics will actually be invisible at a geometric level, but we will still be able to capture it at a categorical level or at an algebraic level. So let me start by introducing the setting. So let M be a Weinstein domain. And phi be a compactly supported exact symplectomorphism. Compactly supported just means it acts as identity near the boundary of M. So let me first give a predefinition. This is a closed version of the symplectic mapping torus. So out of this data, one can construct the mapping torus of phi. Normally, you would take the product of M line. The real line has a translation, the shift by 1, and you model out this product by translation times phi. But I want this to be a symplectic manifold, so I add an extra circle direction. I take the product with a cylinder and do the same thing. So the picture is this. It's a symplectic fibration over the two torus, and it has monodromy phi in minus delta direction. Yeah, and this is not really what I'm studying, but one could also be interested in such an object because there's this slogan that this object turns discrete dynamics into continuous dynamics. What this means is you can pick phi in any component of the symplectomorphism group of M, and when you make this construction, when you follow the flow in this direction, you will find the action of phi on each fiber. So somehow this construction embeds phi into the identity component of the symplectomorphism group of something else. But this type of construction also gives us fillings of contact manifolds. So the open symplectic mapping torus, which I denote by T phi, is obtained by picking a point here and removing its fiber, or rather picking a small ball here and removing its pre-image. You can also obtain it by taking the product of infinitely many times punctured cylinder with M, and you have this translation automorphism on the cylinder again. You take the quotient by translation cross phi. The picture is very similar. This is a symplectic fibration over the genus 1 surface with one boundary component and with monodromy phi in this direction. Yeah. So far, so good. Okay. And so first, let me give an easy remark. The contact boundary, the boundary of this object, is actually independent of phi. And it's the same as the boundary of the product. Or we can also see the product as the mapping torus of the identity of M. This holds because phi acts trivially near the boundary of M, and there is no monodromy near here, so the boundary doesn't see phi. And there's another remark, or let's say a lemma, that I will not really prove, but this is not only an exact symplectic manifold, this is actually a Weinstein domain. In other words, there's a natural level structure on it, there's a natural family of level structures on it, and it's deformation equivalent to a Weinstein structure. So, yeah. Okay. So those are the feelings that we are trying to distinguish, and that's the question. Is T phi different from T0 cross M? And the theorem, the main geometric theorem, says yes, they are different. If phi is non-trivial, in the sense that phi acts non-trivially on Floer homology, on wrapped Floer homology to be precise. And of course, this theorem holds under some assumptions on M, such as vanishing of first Bethe number. Yes.
You said already. What's the purpose of puncturing the torus?
I mean, without puncturing the torus, you don't even have an exact symplectic manifold. So you don't obtain Weinstein fillings of anything without that somehow. Yeah. So there are assumptions on them. Any other questions?
The converse true?
The converse true. What's the converse? If they are different, yeah, I think. Well, wait. If they are different, phi acts non-trivially. Should be true. Should be true. I mean, because if phi acts trivially, well, yes. Yes, actually. I think I will make a remark about this at some point if I remember. So there are assumptions on M, but there are plenty of examples satisfying the assumptions. So one example that I can give is, for instance, take a degree at least 7 hypersurface in CP5, and take a transverse hyperplane section. No, actually the converse is not true, sorry. We can discuss this later. Okay, so I will take M to be the complement of this divisor. This is an affine variety, and it's a Weinstein manifold. And by considering the quadratic degenerations of this hypersurface, you can find Lagrangian spheres in M. And let phi be the 8th power of a Dentwist along such a Lagrangian sphere. Then the conditions of the theorem hold. T phi is different from T0 cross M as open symplectic manifolds, as actually level manifolds. But phi is actually isotopic to identity in the diffeomorphism group. So they are actually diffeomorphic. This is for the other assumptions that would go here. I mean, the assumption that I require is not only this; it's actually the symplectic cohomology vanishes. First symplectic cohomology vanishes, so I don't want lower degree Reeb orbits to increase the dimension of first and second symplectic cohomology.
This is a big twist about what?
About the Lagrangian sphere, about the Lagrangian sphere in M. Yeah.
Any of that different
Yeah. I mean, exact Lagrangian sphere.
Non-isomorphic as Liouville manifolds, is that stronger than asking about them being symplectomorphic?
I think. I mean, the thing is, the result that we are actually proving is the wrapped Fukaya categories are different. So what it proves a priori is just a result that distinguishes the level manifolds. So I couldn't say well, but yeah, I mean, so that the wrapped Fukaya categories are not quasi-equivalent does actually imply they are different as level manifolds, but according to Mohammed, I don't know how the proof of this goes, they are also different as open symplectic manifolds as well. Yeah. This then
You compute this fixed point local homology is it different from tell the user to tell that it's different from identity in a symplectic group.
Fixed point symplectic, sorry, fixed. Yeah, sure, I think so. I mean, there is this long exact sequence, right, of Poisson. Another example of the same sort is for instance, you can take a degree 9 hypersurface in CP7 and again be a transverse hyperplane section. I take M to be the complement of this divisor and phi to be the square of a dentivist. Then similarly, the conclusion of the conditions of the theorem holds. These guys are different as level manifolds, but again for the same reason they are diffeomorphic. And those are not the lowest dimensional examples that I can give, but those are the lowest dimensional examples that I can give in the lowest dimensional exotic examples I can give. So let me give a non-proof.
Can I ask a quick question?
Sure.
Do you know if they're different formally as Liouville manifolds?
I don't know.
What does that mean?
I don't know that.
Well, there's some. You can just think of say the almost complex structure. You can ask whether those two are the same or not on the top of it.
Sorry, I don't know. Okay, let me give a non-proof. This idea doesn't quite work, but it will at least illustrate the main geometric idea behind all the algebra that's coming soon. So assume they are the same. Partially compactify. Meaning we had a hole here, add back the fiber of the hole again, fill the hole, and obtain T5 bar and T2 cross M. So you know there's no a priori reason that those partial compactifications are the same, but let's just assume that we are able to identify the partial compactifications as well. So the picture is this. Of course, we have two fibrations with different monodromies. I'm not identifying them as fibrations, but I'm identifying the total spaces. And so the informal idea is that we will count the circle actions. So on T2, you have an action in this direction, another action in this direction. So you have a Z cross Z word of circle actions. And there's nothing coming from M direction because M has vanishing first cohomology. So they're all Hamiltonian. And so here you have Z cross Z word of them. But here the action in this direction is broken, right? So for generic phi, you have Z word of circle actions, the ones that are only in this direction. The only ones that survive are the ones in this that are going in this direction. So, slightly more precise way of stating this is flux groups are different. I will not tell anything else about flux groups. It's not important for the rest of the talk. And of course, this approach has problems. The major problem is this assumption here. We don't know how to identify partial compactifications. And second problem is less important, but it's still a problem. So even if we succeed, I mean identify partial compactifications and rigorously compute the flux groups, etc. The conclusion would be that the flux group of this guy is also Z cross Z, and that would imply that fiber-wise phi, the action of phi, is Hamiltonian isotopic to identity. Not phi itself. So the isotopy may in general script the projection to the base. Yeah? Everything okay so far? So we will have a solution for this. We will take an algebraic root category phi. Category phi t phi and apply the same idea. Let me write the solution here too. Yeah, or let me not actually write this. Yeah, as I said, the solution is applying the same idea, same program in an algebraic setting. So let me first tell you the categorical construction. So the input is a category, an A infinity category over C actually, and an automorphism, an autoequivalence of the category. And this outputs another category that I call mapping torus category or categorical mapping torus. I will give a motivational definition soon, but let me at least tell you how does actually this relate. So I've already used that word, but there's an invariant of level manifolds called wrapped Fukaya categories, and I denote it by, well, W of M. And the relation of this construction to T phi is in this proposition. It's essentially W of T phi is equivalent to M phi if the input category is the wrapped Fukaya category of M, and phi, the automorphism phi, is induced by the symplectomorphism phi. Okay, I mean, even before I tell the definition of M phi, this proposition tells you that you can compute the Floer homology groups on T phi out of the Floer homology groups of M on M and the action of phi on the Floer homology groups. That's not so interesting probably, but there is also something else. If phi is identity, for instance, this turns into a product and this turns into a tensor product. In that case, this can be seen as a Kunitz isomorphism, and in the general case, this is actually a twisted version of the Kunitz theorem.
What's the twisted version of the theorem that you referred to?
I mean, what it means is, you know, if you have two algebras, for instance, one of them has an extra grading, one of them has an extra, so one of them has a automorphism of algebras. You can take their tensor product, but you can define the product in a way that's defined by the grading and the automorphism. An infinity version of this happened here. I can tell more details. I will not tell anything else about that proposition. I mean, in general, theorems like this, I think, appear in, for instance, the cohomologies of fibrations and so on. Although I learned that from an algebra paper. And so at this point, I can also tell you how I will actually address problem one. So for the problem one, we needed a we needed control over the partial compactifications of T phi. We need to identify T phi bar among other partial compactifications. So after doing this, by using algebraic tools, I will actually be able to show that M phi has a unique deformation. And well, heuristically, and there are ways of making this more rigorous, the deformations of the category correspond to partial compactifications. So the problem of identifying the partial compactification will turn into identifying the deformation of the category here. I will make a remark about this. But let me first give a motivational definition. Inspired by mirror symmetry of it's a broad class of equivalences between algebraic and symplectic words, and let's say we have some symplectic manifold here that I will occasionally denote by x, occasionally by x check, and say I have a symplectomorphism here, and on the B side I have a complex manifold X, and assume this symplectomorphism corresponds to an automorphism here. Okay, so the version of the mirror symmetry that I'm talking about is the homological mirror symmetry that relates, Fukaya type categories to categories of holomorphic vector bundles on this guy, or more generally to coherent sheaves on X. For instance, an example is the punctured torus is known to be the mirror to the nodal elliptic curve. This is by the work of Lekili-Perutz and Lekili-Polishchuk. Yeah. More precise statement in the second paper is the rapid Fukaya category of this guy is equivalent to coherent sheaves on the second guy. And in the second paper, actually, they proved something more general. They proved, for instance, the n times punctured torus is mirror to nodal chain of np1s. Yeah. Okay. So, is it clear when I draw this kind of curves? Is it clear what this means? Okay. So I will make an statement out of this. So you can see here, for instance, the n-fold cover of this guy corresponds to n-fold cover of this guy. I will make this as an informal statement, but I think there are ways of making this more formal. But you would expect the z-fold cover of the left side, which is this infinitely punctured cylinder that took place in the construction, to be mirrored to z-fold cover of this guy. This I denote by T0 tilde. It's a nodal chain of P1s. So, yeah, I mean, as I said, I think there are ways of defining a Fukaya type category for this one as well, but I will not tell anything else about this. And so what this suggests is, after taking the product and applying the same construction on both sides, as a mirror, you expect this construction on the B side. You take the product of X with a projective line, P1 cross X, let's say, and you take the quotient by this relation, T0 by x, or you can also define it in this way. This also has a translation automorphism that moves every curve to the next. You take the product of x with T0 tilde and you take the quotient by TR cross phi.
Sorry, what is psi here?
Yeah, psi is the automorphism acting on the complex manifold.
Ah, okay.
Yeah, I just use different notations for the automorphism acting on the symplectic manifold.
And explicitly in the case of the nodal elliptic curve, is it just some? I guess in this case it's just like I can give you some element of like SL2.
Sure. Sure.
Just some other element of SL2 acting on the elliptic curve.
It could be, but the thing is, I'm not actually taking x to be the nodal elliptic curve. I mean,
Okay.
you can also take it, and in that case, yes, it would be just an element of. It could be just an element of SL2. There's an SL2 action, or maybe a covering of it, an extension of it, action on this side, coming from this side, actually.
So when you say that this picture of mirror symmetry is suggested, is it known that this actually holds? Or is it just...
I mean, you know, this proposition pretty much shows that you have M phi here, and a slogan apparently that's due to gay scoria, but I was told, like Vivek told this to me, is that, you know, I forgot what it is, colimits preserve coherent sheaves. So for this reason, like colimits send sorry, I forgot what was the slogan actually. Like the functor co sends colimits to colimits. That's the slogan. And for this reason, on this side you also have this, you know, by some crazy theorems in int co papers. So yes, if you know this for x and m, yes, you know this. You know the mirror symmetry result, but that's really not what I am trying to show.
Sure.
In my cases, there will be no a priori mirror to M. Yeah. I mean, I'm just trying to give a picture of this construction of M phi. It's slightly different than this. And so at this point, I can also at least verbally tell how to address problem 2. For instance, if you have the action of psi on each fiber here, you have the rigidity of the variety, right? This is not up to Hamiltonian isomorphism or whatever. If, let's say, if fiber by phi, which I denote by, not phi, sorry, fiber by psi, which I denote by psi f, is identity, you can just restrict to fibers now. And that implies psi is equal to identity. It's kind of a tautological in this case. Let's see. Okay, so let me elaborate a little more on the definition of M phi. I will not erase the main theorem for the moment. So to T0 tilde, you can associate a category the natural category that's related to coherent sheaves with finite support, let's say. and I denote that category by O0 tilde dg. And the objects of that category will be the structure sheaves of these curves on the infinite chain of P1s. Sorry. The structure sheaves and twist of structure sheaves. You can also think of this in relation to this infinite cylinder. For instance, you have these Lagrangians that I denote by Li and Li prime, Li plus 1, and the other Lagrangians that are going between two successive punctures. So this, informally, I'm saying informal because I'm not really proving anything formal between cylinder and T0 tilde. This corresponds to Li prime, and this corresponds to Li. Okay? And maybe I should just use this part. So the objects of M phi are, well, I will cheat in the notation to make it look more symplectic, but remember this is a very algebraic construction, so I denote this by Lm, but Lm is just an object of A. So it's like the formal products of these two, meaning just pairs of objects from O T0 tilde and A. And in the algebraic geometric world, this would just be exterior tensor product. And the homomorphisms are defined I'm ignoring the primes here. Sorry. Sorry. Is this anyway? Maybe I shouldn't maybe have written this here. Is this visible here? Maybe to you it's visible. Hopefully. Let's denote this by Lm prime. Is this expression in the corner visible to you? Okay. So the homomorphisms from this to this is defined as this infinite direct sum. It's actually a finite direct sum because for all k except 3 of them, this part vanishes. It's the tensor product of hom tr to the k li, lj, and homomorphisms from phi to the k lm, lm prime. This is a weird construct. This may look like a weird construction. This can be motivated from different perspectives. One way of motivating this is this remark. After making this construction, Li cross Lm is isomorphic to Li prime, Li plus 1 cross phi of Lm. Okay. And let me now state the main algebraic theorem. That's the algebraic counterpart of the first theorem I stated. M phi and M1A are different. I don't have to write are different. They are different if phi is non-trivial. And this still holds under assumptions on A. For instance, the assumption on first cohomology is replaced by the assumption on first Hochschild cohomology, becomes 0. And similarly, I assume HH upper 2 of A is 0. And just the remark, the proposition I stated under the name proposition 2, and this theorem actually imply the first theorem. Yeah.
So I'm still trying to parse this. So you define this M phi. Tell me what the objects are with the Hans. There's some differential there. You say what differential is?
I mean, differential is just coming from the differential of this and differential of this. I mean,
They don't talk to each other?
no. I mean, no. Like, for instance, you can just strictify this. OT0 tilde is by construction a DG category, and you can just strictify A to obtain a DG category as well. And the the differentials don't talk to each other. Mu1 doesn't talk to each other. Mu2 somehow talks, like Mu2 of course talks to each other, right? I can tell more about it. If you stare this in sufficiently long, you will see what Mu2 should be. It's some sort of Grothendieck construction or whatever it's called. And I think I promised you another remark, but I forgot what it was. But sorry. If you remember, just let me know. Okay.
Do you mean the thing about the converse?
Yes. 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 I think I was confused there. Sorry. Thank you. I was confused there. Okay. Thank you. No, that remark. No, there's nothing to remark about it. I don't think there's any reason to expect converse to hold. Yeah. We can talk about this later. Yeah. So. This is actually slightly stronger. As I already told you, this actually implies that the rapid Fukaya categories are different. And a corollary of this, for instance, well, I'm not going to tell this, let me tell this verbally. For instance, if the rapid Fukaya categories are different, if you assume, for instance, M is simply connected, you can attach subcritical handles along the contact boundaries of those guys, along the common contact boundaries in the same way to obtain different fillings of different contact manifolds. They will still be different because this process doesn't change the rapid Fukaya category, but you can actually kill the fundamental groups of T phi and T0 cross M by this procedure. So, what's good about this is at the beginning we had a flux type of idea. It didn't work with this punctured torus. But it didn't work. Flux is in general a subgroup of H upper 1. So even though it didn't work, maybe someone could have hopes that it would work. But in this case, when you kill the H upper 1s, that hope just disappears. In a way, there's no flux here that you can try to distinguish, but it will still, like the same dynamical idea will still hold at an algebraic level. Flux still survive at an algebraic or categorical level. That's the remark that I tried to make.
Do you need that to be Weinstein, or does it just have to have complex boundary?
I need M to be Weinstein for a lot of different things. For instance, for generation theorem, for this proposition, I use the Weinstein assumption. I use the generation by Cocor's thing. And also for the lemma that I stated, for T phi to be Weinstein, I need M to be Weinstein. Yeah. For the algebraic theorem, I don't need anything on M.
David, why do you care about T5?
But do you care about T phi?
I mean, you didn't care there was Weinstein, right? You can distinguish them. Okay, you can distinguish two different Lugol maps.
Sure.
And so there's no Kunitz theorem for Lugol domains?
I mean, ask John Pardon, I guess. I think they still had to use Weinstein assumptions, right? Even for the ordinary Kunitz theorem, not for the twisted Kunitz theorem. I mean, in my case, I will not tell anything else about this. Let me start to prepare for the proof of the theorem 3. Okay. So we will stick to algebraic geometry picture. If you remember, it was essentially this algebraic fibration over the nodal elliptic curve. And it's very well known that the nodal elliptic curve admits a smoothing that I show by combing it. That's actually just, that's smoothing means it lives in a one parameter family of elliptic curves. Around the node, the white curve looks like just union of two axes in the plane, and the neighborhood just looks like a neighborhood of the origin in the plane. And another way of picturing this is, let me write this, smoothing. Another way of picturing this is, you can see this as a family of elliptic curves. In the special fiber, you have this nodal curve. In the generic fiber, you have a smooth elliptic curve. And more generally, you can see this total space. More generally, M phi deforms to what I denote by M phi R. So lemma M phi R is the only non-trivial, of course, non-trivial in the first order deformation of M phi. Up to a parameterization. And let me not cheat here. So by this assumption, HH upper 2 equals 0, the fiber direction here doesn't have any deformations. So there's nothing that's coming from the fiber direction, and every deformation comes from the base direction, and the base actually has only one deformation, that's the state family. That lemma is essentially telling this. And this is the solution to problem 1. Namely, we are now able to identify not the partial compactification, but the corresponding deformation. And another tool that I need is vector fields and flow on M phi on categories on M phi R. So, I will not tell what a vector field is. If you know what this is, a vector field for me is just a HH upper 1 class, a first Hochschild cohomology class. You can algebraically think of the vector field as this algebraic vector field on the Tate family. And this leads to a vector field gamma phi on M phi R. And normally the flow is a family of endomorphisms parameterized by an interval. Here I will replace the interval by something else, by what I denote by SR. SR can be seen as a neighborhood of the nodal affine curve. So these two white curves is the nodal plane curve, ut equals 0. And this is just the neighborhood of that, a formal neighborhood if you want. You can also picture SR in a similar way as a family of curves, where in the special fiber you have the nodal affine curve, in the generic fiber you have an analytic annulus. So morally I'm thinking of this as a model for the analytic annulus, and for me the flow is actually parameterized by analytic annulus. Okay. So flow is a family of endomorphisms G phi parameterized by SR, and it's a solution to an initial value problem, right? So for instance here you have a section that I denote by t equals 1. You have a section of this family. So I ask G phi to restrict to identity in this section. Another condition I have is the flow condition. This follows, I will not tell the meaning of follows, it's too technical. Vector field gamma phi. And the third is a technical condition. In algebra geometric world, this technical condition would roughly translate as the coherence of G phi. Okay. Okay so far? Okay. And the key proposition is the uniqueness of the flow. Unique. So this uses ideas from formal geometry and Polisaida's paper Abstract Analogues of Flux as Symplectic Invariance. So if for instance you have two families satisfying these conditions that I denote by G phi and G phi prime, if they both follow gamma phi, you can consider their homes relative to the base SR. What this means is those are families of endomorphisms parameterized by SR, and hom G phi prime is essentially the transformations from G phi to G phi prime at each fiber. So this is a sheaf over SR.
So I might have expected like a flow to be parameterized by a group, but SR doesn't look so much like a group to me.
I mean, it's like an interval, right? You can also extend it to a group, but it's more convenient to work with affine parameter spaces.
So you really think about it as like the entropy of the infinite chain of P1.
Yes, you can also think of it as infinite chain of P1s, or the deformation of infinite chain of P1s, because it's actually a model for analytic GM, and this is a model for analytic annulus. So this is a sheaf over SR, and that they both follow gamma phi actually imply that this sheaf has a connection. Now, I will not state the formal geometry statements at this point. I'll just draw a picture. Could be a little misleading, but here on the white curve, you cannot move, like you have an isomorphism at t equals 1, right, of this functor and this functor, or this, this endomorphism and this endomorphism. And you cannot really move it on the white curve because there's this node. But when you pass to the generic fiber, on the annulus, you can move it everywhere on the curve, right? So you can move it here, move isomorphism everywhere on the curve. Of course, this is a little informal. Like there are, a lot more rigorous and algebraic statements that I will not really make here. And there is also, uniqueness of the flow, and there is also the existence question, of course. What's that?
Where are we using the phi is not trivial?
You haven't used it yet. I will use it. I will use it when I'm concluding the proof. So there is the existence statement, or rather computation of the family G phi. I mean, I will not really tell the full story. I will just make a remark that for any phi, so you have this section t equals 1, you have the other section u equals 1. Here you have here it restricts to identity, and for any phi it restricts to fiber-wise phi at this other section. The other section can be also pictured here like this. Yeah. This follows from the construction. So the thing is, well, I can tell about this more, but the thing is, G phi is actually obtained by finding a model for the graph of multiplication in TR tilde cross T, like this chain of cube of the deformation of chain of P1s. So maybe unnecessary remark, but yeah. Okay, let me conclude the proof. I don't have any time anyways. Proof of theorem 3. So assume m phi is the same as m1a, and by the lemma that identifies deformations, this assumption implies the deformations are the same as well. And we can actually use the symmetries of this side such that gamma phi and gamma 1A, the constructed specific vector fields, correspond to each other under this equivalence. Okay? Sorry, I'm about to. So this implies by the proposition on uniqueness that the families are the same, or they correspond to each other under the autoequivalence. The picture is like this. You have two families. At the section t equals 1, they both restrict to identity. The family on the right restricts to identity at section u equals 1 as well. But this one restricts to fiberwise phi. So that tells you that fiberwise phi corresponds to identity under this equivalence. In other words, fiberwise phi is just identity, and that implies phi is identity. And that's the proof of theorem 3. And I'm done.